the previous talks, unfortunately, for logistic constraints, but okay. So let me present the work and the evolution of my Conflicts Fellowship. So I started on July 10th, 2018. I defended my PhD on May 14th, 2021, and this was coincidentally my last day of Conflicts. And these are some of my publications. So I understood in Brigitte's email that we should only list officially finished work. But okay, I'm going to talk about some ongoing work and things which are going to be finished soon anyway. Okay, so I'll talk about two topics which I dealt with during my thesis, which are a bit, let's say, not necessarily strictly related, but anyhow. So the first topic is control of free boundary problems. So I already spoke about this during at least the last two meetings, if I recall well. So free boundary problems. What is a free boundary problem? It's essentially a partial differential equation which evolves in a domain which is unknown. So generally, part of the domain is unknown, notably its boundary. This is why it's called a free boundary. And this free boundary, usually we parameterize it by, at least in evolution problems, we parameterize it by a time-dependent curve. And there's an equation which governs this free boundary. And this is how the coupling is done with the main PDE. So a canonical example, not the simplest one or not the most famous one, but a very illustrative one for the works I have done is this piston problem, which was one of the first works was done by Juan Luis Vázquez and Enrique Azulatua. And then it was taken also by Marius Tuxnak, Takehiko Kakahashi, and Liu, where they prove a very nice controllability result, which I will make use of in what follows. And this piston problem, basically, it illustrates a fluid, a one-dimensional simplified fluid moving in a pipe. So you can imagine you have a pipe, and there is a pipe which is bounded, and there is a particle which moves within this pipe. And the particle moves by means of Newton's second law, as you can see in the second equation. So it's coupled with the velocity of the fluid. The velocity is given by Berger's equation. And then you have the continuity of velocities along the particle. And of course, these problems can then be overcomplicated. And this is what people do in aeroelasticity, where basically they don't have Berger's and Newton's law, but rather they have Navier-Stokes and elasticity equations. And then, of course, you have whenever the rigid body or the flexible body is moving, then the domain where the fluid is defined also moves with this. And so these problems are really ubiquitous in many applications. Okay, and the problems I dealt with, the real focus of free boundaries I dealt with during my thesis was the problem of exact controllability. And more specifically, since I was dealing with free boundary problems where the partial differential equation is usually parabolic, I had to deal with a very specific notion, which is that of exact controllability to trajectories, because as you know, you cannot control a parabolic equation to any target because of the smoothing effect. And so the first problem I dealt with was actually the second one, but the first in this presentation is this variation of the piston problem. It's not exactly physically the same, and mathematically it's also different, because as you can see, the continuity of velocities is actually the equation which governs the free boundary. And there is no other additional equation for the free boundary. So the coupling is weaker because it's done mainly through the domain. And the problem we were interested in addressing was to control this PDE to a trajectory of the system, which was not done by then. So a non-trivial trajectory, it's quite a specific trajectory, but non-trivial nonetheless. And we managed to prove that if at initial time we're close enough, so this is a local result, if at initial time we're close enough, then we can find a control which steers the system to this trajectory. And this, by means of, in some specific cases, as Marius pointed out during my defense, in a specific case where some results are done on backstepping, feedback stabilization for similar systems, you can extend this to a global result, in the sense that there exists a sufficiently large time, but at which you can control, but then the initial data is not doesn't necessarily have to be taken small. Okay, I will not discuss the proof. This is something I said last time. And the first problem I dealt with, and the second one in this presentation, is this simplified problem for porous medium equation in one space dimension. On the application, I like to explain which it can model. I mean, it's rather the related thin film equation, but the properties are quite similar. Is that this h, so h of t and x, which is the unknown here, models the height of a thin film, a thin viscous film, as you can see in this picture, which I took from some physics paper. And basically, the problem I was interested in dealing with here is to look at the surface, a contact surface where the thin film touches the solid, and inject some heat. One can assume that has distributed control. You inject some heat, and your goal is not to go to zero, because this is not really what it's not necessarily what you would like if you do some spin coating or something application like this. Rather, what you would like is to bring this film to a more parabolic shape. I mean, this is in the microsphere, but okay. The problem I was interested in was to control this to the self-similar profile of this equation, which after some similarity transformations, you can deduce this to be really a true parabola. So 1 minus x squared, as you can see here. And the result I proved was not in the original domain. So this problem is a free boundary problem in its original domain, but I had to rewrite it by using Lagrangian coordinates to fix the domain. This is also something I did in the previous paper. This is also actually what is generally done, I would say, for free boundary problems up to, I mean, most of the literature I know on control is really to not look in Eulerian coordinates, rather you look in Lagrangian coordinates. You try to exhibit some transformation which depends on the solution, and then the domain is fixed, and you can linearize and you can do analysis in a more convenient way. Of course, this is not the only option, but it's really the most convenient one. And yeah, the result I proved was for this monster equation, because I mean, you can see that there are some singular weights. So rho is 1 minus x squared. So we have 1 over 1 minus x squared. So this is singular near the boundaries -1 and 1. And then you have degeneracy within the diffusion, because 1 minus x squared degenerates linearly at -1, degenerates linearly at +1. But I mean, if you see the equation, still a thing which is nice, even though it's degenerate, is that it's going to admit a very nice variational formulation in a weighted L2 space. And this is, I mean, the main part of my work was really to justify that everything really works in this weighted L2 space. So to justify the boundary conditions, you have to prove some trace theorems using Hardy inequalities. So dealing with these weighted spaces is really not very simple. And it's actually, you can see that then things become even more complicated if you want to do higher dimensional stuff by means of this transformation technique. And the final work I'm actually still finishing this paper. It's a paper we started some time ago on a two-dimensional free boundary problem, exact controllability of two-dimensional free boundary problem. And the point is that the difference with some existing work on fluid structure interaction is that most of the work on mathematical control of fluid structure interaction is done when the rigid body the body is rigid, which means that the equations for the body are ordinary differential equations, which means that even when you do this transformation, you still preserve some coupling. But rather, what is important is that usually these equations for the rigid body, so for the free boundary, will manifest themselves as finite dimensional integrators, and then you can integrate them into the PDE control by means of compactness arguments. And this is actually what I did in the first paper. You use a compactness argument to control the free boundary. Here in this Stefan problem, the complicated part comes from the fact that the free boundary, which you see here, so the Stefan problem is nothing else but a heat equation within a time-moving domain. So in 2 dimensions here, we have horizontally the torus, so periodic boundary conditions. Vertically, we have a boundary control on bottom, and on the top, you have the free boundary, which is unknown. And this free boundary depends on space. It depends on the first, on the horizontal variable. And the problem here is that when you do the transformation to fix the domain, you still are remaining with an unknown which is infinite dimensional. Anyhow, you can still do this transformation. You can linearize, and then you obtain this system, which is quite nice, but it's very illustrative, I believe. And what does this system tell you? Now, this system, if you look at it, if sigma is equal to 0, so sigma is this surface tension which physically adds a coupling between the free surface of a fluid and the fluid velocity. But if sigma is equal to 0, so which means that there is no surface tension, then H, which was the unknown free boundary, is completely decoupled from Y, which is the temperature, or if you imagine a fluid, rather the velocity. Which means that then H can be solved. So you can first control for Y completely independently. You can do this. This is the heat equation. And then you can compute H just by integrating the Neumann trace of Y. But then to control H also to 0 in occurrence at time t, you cannot use compactness because this is not a finite dimensional constraint. This is an infinite dimensional constraint. And so compactness arguments are not going to work. So our idea with the MIT was rather to look at the system and exhibit the fact that we used, first of all, the torus in the horizontal variable, so periodic boundary conditions, and we use a control here, which is along the entire bottom boundary, which means that then when I extend the domain and I put a control which is distributed in the extended domain, the control is still going to be periodic in x1. And so then I can do Fourier series. I do Fourier series and I obtain a one-dimensional problem, which is going to be parametrized by this n, which is the Fourier coefficient, so the coefficient from the Fourier series. And then this one-dimensional problem is quite interesting because if sigma is equal to 0, I obtain the problem, the Burgers problem, which I did in the first paper. So sigma is equal to 0. N is equal to 0, sorry, sigma is fixed. N is equal to 0, which is the first Fourier mode. You can control it by means of the first paper. N is different from 0. Then you have a nice coupling. You have a nice operator, which you can compute the spectrum. You can compute the spectrum, this is not exactly a linear shift of the Laplacian because you have this boundary condition. So the Laplacian on the boundary appears as an n squared. So now there's actually a linear shift, but still you can compute the spectrum by means of some analysis. And then the eigenvalues are quite nice because they behave exactly as what you would like. So like k squared plus n squared. So you can use Moon's theorem and some Fourier series analysis to deduce that this system is controllable. And this system is controllable, but not just controllable, that's actually controllable uniformly in n, which is the thing which matters. You want every Fourier coefficient of the original solutions to be 0 at time t, and you want this to be 0 by means of something which is uniform mn. So because then you can sum up, you can go back to the Fourier series and see that if all of the coefficients are 0, then also the solution, the entire series is 0. And so this is the idea. And then you can transfer this to the nonlinear problem by means of this source term method, which was developed by Marius and his collaborators. So you can add the source term if it decays sufficiently fast at t equal to 0 compared to the cost of control of the system. So you can add these source terms in the equation and then on the boundary, and then you can do a fixed point argument to obtain a result for the nonlinear system. Okay, now second part of my work, interplay of control and deep learning. So this is quite orthogonal, but bear with me. So supervised learning, this is the problem we were considering initially, because this is really the crux, the quintessential machine learning problem. Then there's more sophisticated and fancy work, but really you have to start with the basics. So in supervised learning, the fundamental problem is the following. You have a function which goes from x to y, input to output, and it's unknown. You only know samples of this function, and you want to approximate the entire function. And for logistics, so for specific purposes of how you actually model the problem, how you actually solve the problem in practice, you distinguish the nature of the output space, so the labels y. Y can be either a discrete set of m classes in which we are working with the so-called classification problem. So this can be, for example, if you're typically working with the example of image classification, in which the inputs are a bunch of images and the outputs are labels of these images, in the sense that, for example, you can have images of cats and dogs, and you want to find a map which is going to map an image to the word cat or dog, so 0 or 1, for instance. And then you also have the regression problem, which is quite natural also in this case. what you're doing is that y, the space of outputs, is going to be it's gonna take continuous values. So this can be, for example, a typical application in recent times is the approximation of solutions to partial differential equations by means of deep learning. So in this case, the function you're looking for is the solution of a PDE, for example, Navier-Stokes. You're given a bunch of snapshots, so values. So you have some parts of the mesh, say the boundary or inside, you have different the values of the mesh at different times and the values of the solution corresponding to these snapshots, and you're trying to approximate the entire solution by some machine learning method. And I was not interested in any single kind of machine learning model, but rather specifically neural networks. And really the basic formulation of a neural network is this. Then from this, you can really complicate things and obtain more complicated architectures. But really what it is, when you formulate it in this more mathematical form, is just a sequence of compositions of affine parametric maps. So the WKs and the BKs are parameters, controls in our more familiar language. So these are controls which you can optimize, you can find. And then this sigma is a fixed nonlinear map, which I will assume to be global Lipschitz continuous in what follows. This is the only assumption I will make, unless I say otherwise, is that it's global Lipschitz continuous. But you can see that when written like this, basically what you have is that you have a bunch of initial conditions, xi, and you want to find a control wk, bk, so at every time step, you want to find one control for n, capital N initial data, which are going to steer the initial data. So this composition is going to steer it to the labels you have. And so how do you formulate this in a more optimal optimization framework? As I said, is the following: is that you define some loss, which is going to measure how far you are from how far your prediction, your model is from these labels, from these targets. And then you're also going to add possibly some regularization in order to avoid oscillations of the model. Of course, this is what you would like in principle, because also a goal of machine learning is that you don't only just interpolate xi to yi, but rather you do this in a way that it also works. The prediction also works well for future inputs. So when I formulate it like this, I mean, if I formulate neural networks, I write them down as discrete, these kinds of discrete time dynamical systems. And then I look at this optimization problem, I can see that in essence, what I have, even though my loss function is not just some distance, this is the point in machine learning applications, is that you don't always deal with a distance. You could, but not always. But really what I have is a very compound optimal control problem. I mean, then some people were smart enough, 2016. So, okay, this is a picture I put in my thesis. This is my thesis slides, 77,000 citations. So I looked, this is 2016. I looked yesterday how many citations this paper has, 85,000. So it got 8,000 citations in 3 months. So this tells you, I mean, incredible. Anyhow. So some people were smart enough in 2016 to say to themselves, okay, I mean, I look at this looks like a dynamical system. So what if I add xik here? I fix the dimension. I don't vary over every time step. I fix the dimension. I add some h. Well, what I have is an Euler scheme of a differential equation. And this people, I mean, this has already been observed even in the 80s, even probably even before, but it was observed, but not really much attention was put to it. And some people rediscovered this and found out that this is actually quite efficient in practice. It works quite well. And we thought to ourselves with my advisor and with my colleagues was, okay, let us take this system, or let us take some variations of the system, because you can then change the dynamics however you wish, as long as you keep some similar structure. You have two or more controls. One is a matrix, one is a vector. Then you have this nonlinearity, and you try to see what happens if you study some kind of control problem and to understand what really happens to the dynamics. So we consider these kinds of differential equations. So they call them neural ODEs, or continuous time residual neural networks, or there are many names in the literature. Anyhow, what matters is that you see here, is that you have this kind of a nonlinear differential equation. You have n initial data, but only one control. So it's not like typical open loop control in which you give one initial data, I find one control. Here it's n initial data, one control. This is somewhat the idea of robustness, the idea of generalization behind machine learning. Anyhow, we consider these kinds of systems, and we consider then the continuous time analog of training, which just consists in finding controls which are going to minimize this loss and which are not too violent in some specific norm. And what am I going to assume? So what I'm going to assume is, for now, only there are more results in the papers, but for presentation purposes, I'm going to assume that this loss attains a minimum. So this is not always the case. Actually, for many classification problems, this is not the case. So, but I'm going to assume this constraint, but the results are analogous in the other context. They're just more difficult to write. And the problem we were interested in, naturally from a mathematical analysis point of view, was, okay, we look at this problem. Then if I look at this system, H is equal to T over a number of layers. So in ResNets, usually H is fixed. It can be 0, 5, or 1. In the original paper is equal to 1. So you look here, deep learning. Deep learning means number of layers is big. But this, if I look at this formulation, this is like T big. So from an analytical point of view and from a practical point of view, it makes sense to see what happens when T goes to plus infinity in the trained parameter. So you want to see what happens to the global minimizer of this problem and to the corresponding trajectories when T goes to infinity. And the first observation we had was, I mean, if you have this problem and if you see the specific structure of this neural network here, is that because of its rather homogeneous form, you have a very nice scaling in the equation, in the sense that if I give myself a solution over 0t, then I rescale and I find immediately a solution on 0, 1, which is explicit, as you can see here in blue. And the controls are also explicit. So when I do the change of variables in the functional, then I see that the t comes at the regularization parameter. So another insight we have here is that basically lambda goes to 0 and t is fixed is like t goes to infinity and lambda is fixed. And so we obtain this kind of a result, which we can replace t with 1 over t by lambda and fix t, and then you let lambda go to 0. It's really the same result. And this result tells you that basically the training error, so the error which you want to be 0 by training, is always going to bound it by this polynomial. So it's going to go to 0 polynomial with t. But not only that, then because of the fact that we took a loss which attains its minimum, we can also find a point which is in the minimum in the argmin of the functional, and the trajectories at the final time are going to converge to this point. And not only that, but rather some rescaled version of the controls, so the parameters, are going to converge to parameters which are nice in some sense. So statistically, there are results in statistics which prove that these kinds of parameters, which are going to interpolate, so this is the parameters of the smallest norm in the controllability regime, so in the interpolation regime. So the parameters which are going to oscillate the least, but are going to interpolate your data, well, by training and letting time go to infinity, this is exactly what you obtain. And this is the result we prove. But then, okay, then we look at this. We have no rate of convergence for the trajectory. We have a quite weak rate because, okay, I mean, this is polynomial. We asked ourselves the question, can you obtain something better? And so what we did, let us now consider L2 loss. So not just something which attains its minimum, but L2. But then I will show simulations to show that this is more general. How much time do I have left? Okay. And we add this artificial term. So basically what we do is we pick a target which is going to be in the argmin of the functional. We add it in the system. We add it in the functional like this, and we integrate. So basically this means that at any single layer, at every single time step, I'm going to try to minimize the discrepancy from the output which I want to interpolate. And then the natural result appears after a quite difficult proof, but the result is quite intuitive, is that if you make the constraint of being smaller and smaller at every layer, then this is going to accumulate itself and you're going to obtain exponential decay. And so basically what we have here is that we have exponential decay, in particular at time capital T. So at the last layer, at the last time, at the final time, this is going to be exponentially small, which is significantly stronger. Not only that, actually, the parameters themselves, the optimal controls, are going to be also exponentially small, which is quite important because this means that you're going to ensure some stability in the system. It's not going to be completely violent, and this is actually what we see also in simulations, is that when you have this additional artificial term and you train your network, you train your continuous time, your neural ODE, you see the stability phenomenon. But not only this, you also see that you don't have trajectories which are too oscillatory, because the parameters are going to be exponentially small, which means that you're going to generalize relatively well. And this is what you see here in the bottom picture on the right, is that you recover the original function which from which you sample the data rather well. And here in this picture on the left, we show that this phenomenon of stability over time is not really, it's quite generic for the data, because I mean, we made no assumption about the data, so you can use it for pictures or for whichever application you wish. And this phenomenon has its interpretation in terms of Turnpike, so Turnpike property, but I don't think I have much time to discuss this further. Anyhow, it has a more control theoretical interpretation. And okay, here you see L2 norm for the controls, L2 regularization. And last time I presented, I don't know, Jingzheng, I think, asked me what happens with L1. And I didn't know then, but I know now. So with L1, you put L1 regularization of the control. Basically, what you have is something which you could which you see also in the finite dimensional context of linear regression. So this is the so-called lasso problem. And in the lasso problem, the optimal parameters the optimal solution of what is called the soft thresholding operator, which is going to be equal to something explicit up to a certain threshold and then zero. And this is actually what we see here. And this is what people have there are some results in linear control theory about this fact. This is nonlinear and it's global. So there's no assumption here. We make no assumptions on the loss. The loss doesn't have to attain its minimum. What we do put as a constraint is that we have this L infinity bound on the controls, because if M goes to infinity here, then basically what you have is that you converge, the parameters are going to converge to a direct delta at the origin. So it's going to saturate immediately at the beginning, and it's going to be equal to zero. But what we obtain with Carlos Esteve is that when you have this functional, then there exists a certain time beyond which the parameters are going to be zero. So we have this sparsity in time phenomenon. So the parameters are going to concentrate their values up to a certain time horizon. And then we have this bound on the control law. So it's like the problem without the integral in the state. And I think that this result can probably be improved. I don't know how, but why can I think that this can be improved? Because here we see that at the same time, basically, in many simulations, we saw that at the same time when the parameters vanish, so this T star at which the parameters vanish, then we see that we have this, I mean, of course, when the parameters are equal to zero, given the fact that we have this very specific form of the neural ODE, so if this is zero, then the solution is constant. But the problem is it constant near, is it exactly constant to a minimizer of this E? So if E has a minimum argmin, so if the argmin is not empty, then one could expect that this is true, but I don't know how to prove it. And just to conclude, something which I started doing with Enrique before, so during the time I was waiting for the reports for my thesis, is this problem, which is quite related to the last paper. So this L1 regularization, because we were looking for, so let's linearize the neural network and let's make some assumptions. You can obtain a linear system of this form. And what matters here is that you have an actuator B, which is a vector. So the control here is a scalar. And we asked ourselves the question of what is the optimal B, which is going to ensure controllability of the system. And this problem, I mean, Enrique has studied it with Privat and Trela for many years. They have many very nice papers on this. But the problem, even in the simplest form, in the simplest finite dimensional system with scalar controls of finding the controller B, which is optimal for the controllability cost, has not been solved. Without some specific assumptions, like imagining that the initial data is randomized, so you put some Bernoulli coefficients on the initial data so that cross terms in the Gramian vanish, the fundamental problem has not been solved. And then Enrique had this idea of seeing the system and writing in a Brunovsky form. So Brunovsky, the Brunovsky lemma, the Brunovsky canonical form, basically gives you a change of coordinates of the system. So by means of some, under some other controllability assumptions, there exists an invertible matrix by means of which A is similar to the companion matrix, and you can rewrite this in equivalent coordinates to a system for the companion matrix and the last vector of the Euclidean basis. And then basically what the nice thing is that, okay, when you write this controllability cost, the minimization problem of the controllability cost with respect to B can be rewritten as a nicer but still difficult variational problem. So problem which consists in maximizing the first eigenvalue of some symmetric positive definite matrix. And here is a plot in one dimension. So on the sphere here is the circle, and here I plot for the heat equation described by finite differences 2 points. And we see here very nice properties. We prove some results, and we see some very interesting properties of the system, in particular that uniqueness a priori is not generic. So you can here, you see that there's four maximizers, but the 4 maximizers are quite nice because you can take one and then you have a bunch of symmetries in the system. So it's quite interesting, I believe. Anyhow, this paper is going to come out soon, and I would like to thank you for your attention. And I have to thank Conflex, the Conflex network, for the great courses we had, and for financing my thesis. And thank you. Yes, thank you.